Hola a todos. Hello, everyone. It is my pleasure to introduce Dr. Igor Mekhov from St. Petersburg State University and visiting the University of Oxford. Igor did his PhD in the State University of St. Petersburg. Then he moved to Innsbruck and did a postdoc with Helmut Rich. Afterwards, he was a fellow at Harvard with Eugene Demmler. And then he led a theory group at the University of Oxford, and now he shares his affiliation between St. Petersburg and Oxford. Igor will talk about open quantum systems beyond dissipation, which is about weak measurements, feedback phase transitions in many body systems. And now I give the word to Igor so that he can talk to you guys.
Hello, thank you very much, Santiago, for this invitation and for the introduction. Yes, so I will start my talk. It is quite unusual when I don't see you and don't hear you, but let's proceed like this. So I will be talking about open quantum systems, which, however, are not necessarily dissipative. So I will be talking about weak quantum measurements and phase transitions due to feedback in many body systems. And I would like to, I'm really grateful for my long-term collaborators, Santiago and Denise and Tatiana Ivanovs from St. Petersburg. So our general motivation is the following, to consider open systems and ask questions beyond just dissipative systems. We all know that quantum phase transitions is a very well-known thing, very well-known phenomenon. Typically, it is considered in closed systems and can happen even at zero temperature. So these are truly quantum fluctuations which drive quantum phase transition. To describe these transitions, we are typically interested in change in the ground state of a Hamiltonian. The notion of quantum phase transitions has been generalized for dissipative phase transitions, where we consider open dissipative systems. And these are the fluctuations due to the coupling between the system and the environment which drive these phase transitions. And instead of ground state of a Hamiltonian, we are interested in the steady state of master equation. Now, the field of dissipative phase transitions is a very well-established field now. There are many works and there are plenty of phenomena which were predicted and obtained. And now it's time to ask a question: what can be the next step to advance this direction further? So we propose to consider a system which is controlled by feedback. So we consider quantum measurement and feedback control. So the system is open, but not dissipative. It is controlled by feedback loop. And I will discuss that we can find a phase transition, which is induced by feedback. And the fluctuations which drive these transitions are due to the fundamental quantum noise, the noise of the measurement, which originates from the incapability of any classical detector, of any classical device, to capture quantum superpositions and entanglement of the quantum world. So instead of considering master equation, typically we're interested in stochastic master equations and describe these effects in terms of quantum trajectories. Indeed, quantum measurements and dissipation are related to each other. And if we keep track record of all measurements of our system, we can get quantum trajectory, quantum measurement. But if we don't keep track record, and in mathematical language, if we average over all possible measurements, over all possible quantum trajectories, this is the way how dissipation can be described. So in this work, we are specifically interested in the phenomena which are visible at the level of single trajectories without necessity to take average. And in contrast, if we average or solve master equation, many phenomena which we discuss here can be difficult to visualize actually. So we are really interested in the phenomena which appear due to the quantum measurement and feedback loop. So this is the outline of my talk. First, I will discuss feedback control and introduce feedback-induced phase transitions, which are generalizations of quantum phase transitions and dissipative phase transitions, because as I told you, dissipation is actually a special case of quantum measurement when we don't keep a track record of the measurement. Our goal is to shift the paradigm of feedback control from the control of quantum states to the control of phase transitions. I will show that feedback enables tuning the quantum properties of phase transitions, and in particular tuning the universality class of phase transitions by tuning the critical exponents. And this gives rise to novel type of quantum simulators of quantum baths, which are useful to simulate different quantum materials and also to obtain novel type of time crystals. So this will be the first part of my talk, and I will present results for other general system, which is here. So I will make a pointer. So I will consider an ensemble of two-level particles, or spins, or qubit, as you wish. So rather general setup. In the second part of my talk, I will present you result for a specific system of ultracold atoms trapped in optical lattice, which interact with light. So this will be already a many-body system, and I will show that weak measurements constitutes a novel source of competitions in many-body systems, and due to this competition, one can obtain novel phenomena and novel states of bosons and fermions. For example, macroscopic oscillations of bosons, protection of fermion pairs by measurement, and generation of antiferromagnetic order, again, just due to the measurement process. So, what is feedback? Indeed, this is a very well-known concept. When we measure something, so here we will consider light, which interacts with our atomic system. Depending on the measurement outcome, one can change the system parameters and close the feedback loop. And feedback is indeed a very general phenomenon. It is used and known not only on physics, but also in engineering, and even used in modern rock music and contemporary music to produce some unusual noises or unusual sounds. We can look on this combined system as a case of hybrid quantum classical system. So what are hybrid systems and why they are popular? The idea of using hybrid systems is to use advantages of both components, and hopefully to avoid disadvantages of both components. So in the language of hybrid systems, here quantum system will provide quantum superposition. It can provide multipartite entanglement and also provide large Hilbert space for our combined system. On the other hand, other rather complicated properties can be provided by classical systems, feedback loop, so nonlinearity, non-Markovianity, and fluctuations. As a result, the compound system, the hybrid system, will have all these properties together. The system of feedback has several advantages and interesting properties, which can be used even further, well beyond the topic of this talk. For example, already now the feedback is digital and very well programmable. So this property basically we use already in our work, that feedback can be made digital. In addition, feedback is scalable to multi-channel operations. So one can measure many signals, many properties of the system, and also operate on different variables of the system. And the process can be parallelized. So many operations can be done in parallel. And therefore, we believe that this setting is a perspective one to develop the direction of quantum artificial intelligence. So first of all, several words of what is actually measurement back action. How does it appear? So we all know that two-level system, qubit, spin, atom, can be represented via the block sphere. So if the system has two levels, excited and ground state, in quantum physics, there are also superposition states which are in between on this Bloch sphere. And generally, the pure state, is given by the superposition of excited and ground state with some coefficients. Now, let us consider light-matter entanglement and light-matter interaction. So, in the simplest case, we can say that if the atom is in the excited state and there is no pump, so if it is in the excited state, there can be 0 photons emitted. But if the atom goes to the ground state, one can observe 1 photon which can be emitted. So this is the origin of the light-matter entanglement, and we see how light and atom are interconnected. Now, what is the measurement back action in this very, very simplified situation? So if we measure 1 photon here, we will know that the atom now is in its ground state. So basically, by the detection of single photon, we will project our system, our atom, to the ground state. So by measuring one of the subsystems light, we back-act on the atomic state as well. Similarly, if we do measurement, but we don't detect photons, we assume that the atom is in excited state. Now, let us summarize how the state can be changed. First of all, of course, even without any measurement and dissipation, the state can change by unitary evolution, for example, by Rabi oscillations at the Bloch sphere. The second case, which I considered, is projective measurement, so the state collapse. If we measure 1 photon, we project the atomic state to the ground state. And additional possibility is to use weak measurement, which gives us partial knowledge about system. So we don't detect 1 photon for 1 atom, but still we can get some information about the system which is not complete. For example, if we have ensemble of atoms, many atoms, some of them are in the excited state, and if we detect very small number of photons, we know that state changes. But we know that the atoms don't go to the ground state. So this can be described in terms of quantum trajectories. So every detection of photons for ensemble will change the state, but detection does not mean full collapse of the system. So now the measurement results in quantum physics are stochastic. And we can, if we measure the atomic state, sometimes we can measure that the atom is in the excited state. Sometimes we can measure that the atom is in the ground state, if it is in the superposition state. And this actually gives the measurement back action and also measurement noise. And again, this is a property which says that our classical detectors are incapable to capture the entanglement of the quantum system. And in our case, it is this measurement noise which will drive phase transitions, which I will be discussing during this talk. So I will show some quantum trajectories. And again, as I said, quantum trajectories can correspond to weak measurements or imperfect measurements. If we look on this situation, if there are photo detections, so we can introduce quantum jumps, which change the system. And interestingly, if we don't detect anything, the state can change as well. Why? Because if we don't count any photons, we get information that probably atoms are not excited at all. So even when we don't count photons, we get some information about the system, and the quantum state of the system changes. So indeed, quantum measurement and also feedback control are well known in quantum physics and quantum optics in particular. This is a typical goal of quantum metrology, which is interested in preparing some interesting states of spins, for example, by the measurement and feedback. So by the measurement and feedback, you can move the Bloch vector to some point and, for example, squeeze the fluctuations by measurement, which is indeed very interesting. But here we want to change our point of view. So we want to change the goal. We want to shift the paradigm of feedback control from the control of quantum state to the control of phase transitions. And in quantum metrology, quantum noise is indeed very important, but after all, it plays a rather negative role because it limits the performance of quantum metrology. You cannot beat the quantum noise limit. In our work, quantum fluctuations, quantum measurement fluctuations, measurement noise plays essentially positive role. So often we will want to have a lot of fluctuations in the system because these are the fluctuations which will drive the phase transition in our case. So let us discuss the model which we consider. As I said, we consider ensemble of two-level systems which interact with light. So to simplify the situation theoretically, I will consider only single mode cavity. So some pump illuminates the ensemble of qubits, and then light leaks from the cavity and is measured. In this part of the work, we will consider the measurement of the quadrature of light which leaks from the cavity. Without feedback, this is a well-known system, so it's a decay model which is used in cavity QED. This is the Hamiltonian, and here A is the annihilation operator of the single cavity mode. SZ and SX are the spin operators of particles inside the cavity. Omega R is the frequency of the qubit. G is the light matter coupling constant, and N is the number of particles. For our work, it is important that we consider here a super strong coupling regime. So what is super strong? This is the regime where we cannot use the rotating wave approximation. So we need to use this term as a whole. We cannot neglect any term here. As for example, in the strong coupling regime, we can neglect some terms in this expression. So now let us introduce the feedback in the system. So before going into the details, what is this term? I would like to underline that it looks like Rabi frequency in the Hamiltonian. So if we will think about two-level atom, which is driven by external light, so in front of the SX component, we will have a Rabi frequency. But in our case, this will be an operator. And for feedback, we can represent this term in the following way. So we measure quadrature outside the cavity in time. Then, in general, we can take some nonlinear function of this quadrature, and then we convolute history of the quadrature in the past. So we take integral with some kernel h, and this is our signal which we use in the Hamiltonian back. So we measure light, we calculate a nonlinear function and integrate over the history of the emitted photons, emitted light. So this is how feedback is introduced in this problem. Now, what is the experimental status in this field? So the first decay phase transition was obtained at ETH in the Tillman-Esslinger group in 2010, and it wasn't obtained with atoms or spins, it was obtained with Bose-Einstein condensation. And how the phase transition looked like, so the BEC in the cavity was pumped, it was homogeneous in space, but above the phase transition, the checkerboard pattern was observed. So the atom appeared either at odd sides or at even sides. So either one checkerboard pattern or another checkerboard pattern. So this was the first observation of decay phase transition, even though it was predicted in the 1970s, so many decades ago. And indeed, in this case, there were no two-level atoms, but the two effective states were two momentum states of BEC. So basically two matter waves which propagate in front each other, and the ground state is the BEC with zero momentum state. So then this system was extended to optical lattices, and many body states, so not only molten solid and superfluid, but also density waves and lattice supersolid were obtained. And this year, there was a first realization of feedback control of decay phase transition, again at ETH. And indeed, the feedback assisted to obtain decay phase transition with some interesting properties. And indeed, I should mention several other groups which work in similar directions of cold atoms in a cavity. So let us continue with theory. So we have this Hamiltonian, which I introduced. And this is the feedback signal. Now we can easily write the Heisenberg-Langevin equation by Heisenberg. So Heisenberg-Langevin equation describing cavity mode like this. So we see that there is some detuning from the resonance delta, and indeed spins affect the light in the cavity. So kappa is the decay rate of the cavity, and Fa is the noise, quantum noise, which indeed is present in the cavity if the cavity is open and it decays. Now I will give some hints, not a very careful theoretical derivation to save the time. So we can assume that light mode can be adiabatically eliminated from this equation if the kappa is very large. So in this case, we can roughly assume that light is proportional to the spin. And again, this is not a careful theoretical derivation at all. These are just hints, but these are helpful hints. Now, if light is proportional to the spin Sx, we can see that we can think that we can substitute this light in this integral and then further in the Hamiltonian. And we will see that in the Hamiltonian, we will get the term which looks like a spin-spin interaction. But here, due to the feedback, which is delayed and has a memory in this integral, we see that this is some kind of effective spin-spin interaction in time. So spin interacts with itself in the past. And this term resembles the spin-spin interaction, which we often introduce in space. For example, in spin chains or in continuous systems, when two spins or the spins interact in space, in real space, not in time. So this is indeed just an analogy, but apparently this is a very useful analogy. And it has been already used, for example, in theory of spin boson model. Now let us consider some details. What kind of effective interaction which we can obtain if we change this feedback response function h. I will give some examples. So this is the feedback integral. And of course, the simplest case is when the feedback is instant. So this is Markovian feedback. There is no memory in feedback at all. And then this interaction will give the spin-spin interaction as squared. And this would correspond to the Lipkin-Mishkov-Glick model. And actually, this is exactly the case of decay phase transition, which has been already observed at ETH. Now, we can use another functions h of t. For example, we can use the train of delta functions. So it's a delayed signal with several delays, several delta functions. And we can also shape the amplitudes of all these delta functions. The interaction term will look like this. And this term indeed looks similar to what we typically study in spin chain systems, for example, with Ising type interaction, where the spin-spin interaction decays algebraically with the distance between spins. Here we have a similar system, but the spin-spin interaction decays algebraically, possibly algebraically, with the delay between two components of h functions which were introduced by hand in the feedback loop. Another possibility to use this temporal function with algebraic decay, so without delays, without delta functions. And in the calculations, which I will show you, we actually will use this function. It turns out it is interesting possibility because similar cases, but not with feedback, but with the baths, were considered in the context of spin bath models. For example, spin boson model, Caldera-Leggett model, Kondo models, or model of quantum Brownian motion. And apparently, the feedback can model similar response function and also similar spectra of the baths. And an experiment, it is extremely difficult to build a simulator of a bath with a real bath where frequency function, so the frequency response function will change according to some law, some power law. There are indeed some works about this, but this is indeed difficult. But here with feedback, we can just change this H function on a computer, because as I said, feedback is processed digitally, and obtain various functions which would correspond to different frequency response functions. So it's interesting that indeed we can also introduce the exponential decay, which will model processes in the cavity, but it turns out that in our work this is not very interesting at all. So there are not so many interesting new effects which we can obtain if we use this exponential decay. The algebraic decay is much more interesting, and why it is interesting, we can think, just to get a hint, we can think about spin-spin interactions in spin chains, and indeed the algebraic decay is much more interesting than exponential decay, as in many-body physics. So just to summarize advantages of feedback, so we can build quantum simulators to simulate not just quantum systems and not just open quantum systems, but simulate quantum baths. We can also think about creating novel type of time crystals with interactions of spins in times, because typically in the field of time crystals, what is change in time is some constant, and the change in time is given a priori, basically by hand. There is no internal interaction. Here we can introduce this time interaction in time. And we can simulate a plethora of phenomena in a single device without modifying really the device, because several interactions, which I discussed here, can be introduced simultaneously just by taking some complicated form of the function h. We can also increase nonlinearity in the system in a straightforward manner. And again, I would like to understand that all effects which we considered are beyond the cavity-induced autonomous feedback, which is just feedback with exponentially decaying function. So, as I said, we start with this decay Hamiltonian with feedback included. Now I skip theoretical formulas. I just want to say that we use Holstein-Primakov representation of the spin operators, and in simple terms, it can be thought as just linearization of the problem. So instead of having nonlinear spins, we will consider linear dipoles with the quadrature x. And so this corresponds to the bosonization of spin operators. Now, using Heisenberg equations, we can derive the second order Heisenberg equation for this quadrature of spins, so of linear dipoles or matter waves in the case of BEC. So we see that this is equation, nothing but equation for the harmonic oscillator, but with some memory tone, and also the noise in the system will be non-Markovian due to feedback, even if the leakage of photons is typically Markovian. So after the transformation, the noise for the matter quadrature will become non-Markovian. And this is an equation which one can meet in the theory of Caldera-Leggett model and quantum Brownian motion. So above some threshold, there are instabilities. So there is a phase transition when the feedback coefficient, so this is a feedback gain, reaches a critical value. Below this value, the expectation value of the quadrature is 0. Above, it takes non-zero values. So I will show now you some quantum trajectories. And here I show the quantum trajectories of the conditional variable, conditional quadrature for two choices of functions, function h with algebraic decay. So this is a very quickly decaying function. The power is 20, so it's almost instant decay, almost Markovian feedback. And here the decay is very slow. So when the system is far from critical point, we see nearly the same dynamics. There are oscillations. And when we go close to the critical point, in this case, the fluctuations increase. Whereas in this case of almost instantaneous decay, we see the decrease of the oscillation frequency, which has been observed in decay phase transition, and it is called mode softening using the condensed matter terminology. So above the phase transition, the system gets unstable in both cases, and as here we consider non-linear linearized system, we don't have the steady state at the end. Now we observe these coherent oscillations, which means that at a single quantum trajectory level, the state is not zero, as I showed, as I said here, for the unconditional expectation value. But for conditional expectation value of the quadrature, we see oscillations, which means that there is already macroscopic coherence in the system, even below the transition threshold. Now, I will come back to this type of oscillating trajectories later in my talk, when I will consider ultracold atoms and optical lattices. But for the moment, the result is that, first of all, feedback can induce phase transition with growing amplitude. And now I will show that feedback can change not only the critical point, which it can, but it also can change really quantum properties of the phase transition, that is quantum fluctuations. So here I plot the unconditional value of the fluctuations of atomic quadrature x squared, and we see when we approach the phase transition, the divergence for different h exponents is different. And we can characterize this by introducing the critical exponent. So we can approximate x squared by this simple form and find the critical exponent. So what we find is that critical exponent of x squared depends on the exponent of the feedback. And this is indeed very important. So feedback can change the type of fluctuations in the system. It can change the critical exponent, and thus it can change the universality class of the phase transition which we have here. So just to summarize this part, the critical exponent is tunable due to feedback control. And this is not achievable simply by using cavity. This is really the algebraic decay of feedback function which gives this effect. And feedback creates the coherence even below the threshold. Now, if we use numerically the nonlinearity in the system, so without bosonization, without Holstein-Primakov, we can observe phase transition in this form. So we see that above phase transition, indeed, there is some stationary state. In the nonlinear system, the growth is not infinite. It reaches some value. And this looks similar to the spin boson model, where people study localized phase above phase transition and so-called delocalized state below phase transitions when average spin is 0. What is more interesting, and it will be interesting to study this in the future, that it is not necessary to use non-linearity of quantum system as wins. The quantum system can be actually linear, and the non-linearity can be brought by feedback itself. So quantum system can be really, really simple as linear dipoles and just give the quantum coherence, quantum superpositions, and nonlinearity and all other interesting things as Markovianity can be taken by the feedback loop, which is classical, so also relatively simple. So now I will consider most which are trapped in by optical lattice, possibly inside the cavity, but this is not necessary for all phenomena which we discuss here. So we can avoid the use of the cavity, or cavity can be not extremely high Q. So the photons which are scattered from atoms are detected, and we will observe how the atomic state changes when light is detected. Because as I explained to you, light and atoms are entangled, and like an EPR scenario, if we measure one part of the entangled subsystem, light, we also project the second part of the entangled subsystem.
Okay,
So,
Igor, just a minute. Guys, are there any questions of the first part? Sorry. I was having problems to unmute. We have a question, Igor.
yes.
From the first part. Do different results can be gained depending on the type of atom that you choose, for example?
So, yes, we consider the really simple situations, two-level atoms. But indeed, if we introduce some multi-level atoms, for example, then the situation will be even more interesting.
Okay. Well, that's it, and then we give you more questions at the end of that part.
Okay. Okay. Great. So here I will be mainly focused on the measurement back action, and only at the end I will show some results about feedback, because here I will actually present you some results which we obtained already some time ago. And now for us, it is like a second round. Now we are interested to see can we obtain feedback-induced phase transitions in these many-body systems, which we considered before. So here I will show that weak measurement, which are not fully projected, so just some photons are detected, not they don't give information about the all atoms at the optical lattice. So I will show that the weak measurement constitutes a novel source of competition in this many-body system, in addition to tunneling and atom-atom interaction, which are usually considered. And this competition gives rise to new states and dynamics. For bosons, I will briefly mention the macroscopic oscillations of matter waves. And for fermions, I will show the protection and breakup of strongly interacting fermion pairs, as well as the generation of antiferromagnetic order by measurement. So what was our really general motivation to study this system of cold atoms interacting with quantum light, so quantum optics of quantum gazes? The general motivation is the following. We all know what is classical optics. It considers light as classical light waves, and different material devices like beam splitters, mirrors, diffraction gratings are used to manipulate these classical waves. In atomic physics and in quantum optics, we usually consider atoms which motion is totally classical. So atoms are just like balls which fly around and interact with light. So the motion of the atoms is not quantized at all. But quantum optics indeed considers some very interesting quantum states of light. In contrast, there is another field which is called atom optics, which appeared in the 80s due to the development of laser cooling techniques. And the role of light and matter in atom optics and in classical optics are completely reversed. So the matter waves are now behave as light waves in classical optics, because atoms are very cold. The de Broglie wavelength is huge, so these are really like waves. And instead of material devices, which I mentioned here for optics, these are forces of light which are used to manipulate the matter waves. And after the Bose-Einstein condensation and Mott-insulator state of ultracold atoms were obtained, this field of atom optics developed into quantum atom optics, where the quantum properties of matter waves became very important. But I would like to underline that still up to now, the role of light in all these field is to manipulate classical devices as beam splitters and mirrors. I will show you this on the next slide. So basically, this is a very well-developed field of ultracold atoms. The optical lattices are used to trap atoms, but the light is essentially quantum. And for us, it was very interesting to see what kind of new phenomena one can find if in the field of quantum, ultracold quantum gazes, we will consider the quantumness of light as well. So for those who are not very familiar with cold atoms specifically, just several analogies. So in optics, we all know that there are mirrors, diffraction gratings, and lasers, which show interference patterns. The light can be trapped by cavities, and very similar effects can be obtained in atom optics. So an atom can be reflected from the, we can say, mirror, which is formed by light beam. So the atomic beam can be diffracted from the standing wave of light, and the analogy of cavity for photons are the trapping potential. So either traps optical lattices, which can trap quantum states of atoms, and these states can be then manipulated. These matter waves, which are trapped by laser light, can show the interference, if this is a superfluid state, for example, very similar to the interference of light waves here. The only important thing which I want to underline, if we think about effective cavities for atomic waves, here we see that in optical lattice we can have hundreds or even thousands of small cavities for matter waves. Whereas in optics, to build thousands of cavities, it is possible, but it is indeed rather challenging task. And again, I would like to underline that in the field of optical lattices, the laser light, which is used here, is completely classical. Quantum properties are not important at all. So if we move to the quantum optics and quantum atom optics, we can say that in quantum optics, we consider operators of light amplitude, not just C numbers as in Maxwell equations. And in quantum atom optics, we consider the many-body wave functions, which are conveniently expressed in the formalism of the state operators, and the formalism of second quantization, for example. So this is how theoretically we go from atom optics and optics to quantum optics and quantum atom optics. And in both these fields, the effects, similar effects, which were predicted and proposed by famous theories, were already discussed. So, for example, Fock states, Glauber coherent and squeeze states, and Schrödinger-Cat states. This shows that indeed fields of quantum optics and quantum optics are related to each other. Now, I will consider a very, very simple model for light scattering. So, some light beam illuminates atoms in an optical lattice and is scattered. So obviously the amplitude of the scattered light in the simplest case is given by this expression, which is nothing but sum of contributions from all atoms at lattice sites. So this is just an integral of atomic density operator with mode functions of the laser light, which can be exponents. So just traveling waves, for example, with exponents here. Now, we use the second quantization formalism. We introduce the state vector for the for atoms, and we observe. So we introduce Fourier functions here, as is typical in the cold atom physics, where B is the annihilation operator of an atom at site I. If we substitute this expression into this integral, we give again a very simple result that amplitude or operator, indeed, of the scattered light is proportional to this D operator, and this is simply a sum of atom number operators at each site with some coefficients which are important in this work, which depend on the geometry of optical waves. It depends on the angles, for example, between different waves. So this expression describes nothing but diffraction of light waves from periodic pattern of atoms. It is very well known. But indeed, these n are operators here which can fluctuate. And for us, the most interesting effects happen not at the position of Bragg angles, which is a classical effect, but between the Bragg angles, so at the angles of diffraction minima. And if we think what are the diffraction minima, we can say that atoms at the lattice scatter light with different phases. And we can find several groups of atoms which scatter light with the same phases, and then another groups of atoms which scatter light with other phases, possibly with opposite phases. So the simple example is the following. If we consider just 90-degree geometry, as I show here, the atoms at odd and even sides scatter light with opposite phases. So here we have plus minus 1 in front of the n operator, which we can simply rewrite as the difference between atom number operators at even sides and odd sides. So this shows how we represented our extended delocalized system only in terms of two modes, atoms at odd sides and atoms at the even sides. And then what I will show next, just a summary of some results, this difference corresponds to the spin component of the spin operator, which I discussed just before in the part of the talk devoted to feedback control. So, just depending on the notation, it can be either spin X, Y, or Z component. What is important here that we consider the global light scattering, but due to this optical geometry, the phase of light changes from side to side. So we see that spatial structure of the scattering and thus measurement of light enables the competition between global and short-range processes. The short-range processes are just tunneling between neighboring sides, but as we see now, even global light-matter interaction can compete with these short-range processes because, again, the splitting of mode is between odd and even sides. So two modes are basically included inside each other like this. So just some results. So first of all, again, I will show results only for the simplest case of odd and even sides. So two modes of atoms, atoms at odd and even sides. So if we just push a little bit this system in optical lattice, what we observe, we will observe the oscillations of atom number between odd and even sides with a very small amplitude. And if we think about the distribution function, it will spread. So here I plot the distribution function of atom number in one mode, so let's say odd sides. And we see that the distribution function spreads, but the amplitude imbalance between odd and even sides will be very small. Now, if we apply the quantum measurement and simply count the number of photons which leak from the cavity, we will measure this atom number difference. And what we see that this atom number difference, which for unperturbed system is around 0, indeed, we see that this atom number difference starts to oscillate. And what is interesting, the amplitude of oscillations reaches its maximal value. So just performing the measurement at 90 degrees, we see that there is a total exchange of atoms between odd and even sides. Also, again, this is a distribution function, so it has its width. We see that due to the measurement, there is a squeezing of this variable, which potentially we can expect because usually measurement squeezes the variable. But what is more interesting, the measurement pushes, the quantum noise of the measurement pushes the system to oscillate with very large amplitude. And if we consider more modes, we can obtain, again, the well-defined modes, 2 or 3 modes, but I will discuss this now. So it is possible to obtain really interesting effects of oscillations. Now, the message from the slide that the variable which we measure, the atom number difference, starts to oscillate. But indeed, we can make the system more interesting and measure other variables. So for example, here we take fermions, not bosons, and we'll measure the staggered magnetization of fermions on a lattice. So first of all, we use this idea to measure the atom number difference between odd and even sides, because these two modes scatter light with opposite phases, the phase pi. And using different polarizations of light, it is possible to measure the magnetization here, number of spins up minus spin number down. And again, as in the previous case, so we can combine this magnetization and this variable into the staggered magnetization. And again, we see that what we measure, the variable which we measure, staggered magnetization, starts to oscillate and reaches its maximal values. And what is the maximal value? This corresponds to the maximal staggered magnetization. That means antiferromagnetic order, which is generated simply by measuring the photons leaking from our system. Another example, here we consider strongly interacting fermion pairs which sit on the lattice, and we perform some measurement of some variable, and we see how the atom pair tunnel. So here we see that these fermion pairs start to tunnel in pairs, so we see only even numbers are possible. And if we measure something, for example, density, we see that there is a breakup of fermionic pairs, because, and this is quite obvious, simply because measurement introduces some noise, and noise destroys these pairs. This is rather obvious. What is less obvious, that by measuring the magnetization, we can protect fermion pairs, because the measurement of the magnetization will squeeze the uncertainty in our system, and thus the magnetization will be squeezed, and so it will be zero. So basically the fermionic pair cannot break up, otherwise the magnetization will grow. And I would like to underline that these are really dynamical effects due to the weak measurement and the competition between weak measurement, tunneling, and interaction. And this is not really a quantum Zeno effect, which is well known. Very strong projective measurement would not lead to the oscillations. It will just freeze any dynamics. So now we actually considered feedback on these systems. And so here I show again the bosonic oscillations, which I showed you before. And
Igor, there's one question. Sorry,
yes.
This is all without feedback, right? So it's just measurement.
Yes, exactly. So this was just measurement, and here I show the slide with feedback. Exactly. So we showed that when the feedback strength increases, goes over some critical value, these oscillations can be stabilized. And at that time, we did not thought about this in terms of phase transitions and quantum properties of the phase transitions. We used just Markovian instant feedback, but nevertheless, we already showed that freezing this state is possible when we go above some critical value of the feedback strength. And the perspective, it will be interesting now to think if we can use the approach of feedback-induced phase transitions, which I explained in the first part of my talk, if we can use these effects to obtain phase transitions in other systems, not just in the ensemble of two-level atoms or BEC without optical lattices, it will be indeed interesting to see what kind of phase transitions and we can obtain for ultracold bosons and fermions, for example, the oscillations and systems which I showed you just before. And moreover, it will be indeed very interesting to check if we can tune really quantum properties of the phase transitions. In particular, well, can we tune the universality class of these phase transitions? Can we change the universality class of antiferromagnetic order, for example, which was generated by quantum measurement? So now I would like to conclude. I have shown that back action of weak measurement constitutes a novel source of competitions in many body systems, and measurement back action can compete with, for example, tunneling and atomic interaction, which are typically considered in the context of ultracold atoms. And this competition, usually competitions in the system bring something new And indeed, we can obtain some new effects like oscillations of bosons and protection of fermion pairs and the generation of antiferromagnetic order. I have also presented you the feedback-induced phase transitions. And these transitions include quantum and dissipative phase transitions as special cases. I showed you that concept of feedback control can be extended to control quantum phase transitions. In particular, it can be used to tune the universality class. And this can lead, hopefully, to new generation of quantum simulators to generate quantum bars. And if we can generate different quantum bars, then we can generate some real quantum materials and also consider some new type of interacting time crystals. So thank you very much for your attention.
Thank you very much for your very nice talk, Igor. And I don't. Are there any questions for Igor now, guys? You can ask in the. You can raise your hand, and then we can ask Igor some questions.
Yes, I'm gonna unmute everybody now. Thank you so much, Professor Igor, for your seminar. I'm gonna unmute everybody in case you wanna discuss something right now. And after that, I have to give you some announcements, but before, you can ask freely. Probably you need more with your voice, you feel better about it. I don't know, somebody else who wants, Rocio, one question from Rocio.
So have you, Rocio asked, have you considered different kinds of weak measurements?
So in the second part, we considered the measurement of photons, photon detection. In the first part, so in the results which I presented, we considered quadrature measurement. So these are two types of the measurement which we considered, and indeed photo detection can be considered as well to obtain feedback-induced phase transitions.
Anybody else? Nope. Guys, you are very shy. So, yes? Nobody? Okay, thank you so much, Professor, again for your, yes.
Very much.
Okay, Eduardo, wait, there is somebody else. There is a technical problem. There, Eduardo.
Yes, hi, I have a question. I couldn't fully understand the measurement part because you have some light there and you're scattering photons. Those photons will be there anyway. You want to see, for example, the stagger that you were saying.
Yes.
But, it sounds to me that from what you're explaining, the fact that you're measuring is what drives these staggering states and these oscillations.
Yes, exactly. So when we take into account the measurement and so if we take into account the measurement, so as I explained, if we take into account the measurement protection, so the projection of the atomic state when light is detected, the atomic state is perturbed by this measurement detection. And this is exactly the noise which pushes the system to oscillate.
So what I'm trying to understand is, in order to see this staggering, probably I will need to put a mask on the even and on the odd atoms, for example. So let's say that I put a beam splitter and I put a mask to see only the even, and I put on the other side of the beam splitter a mask to see only the odd ones.
So you can think in terms of masks, but in fact this mask is realized automatically. So when you shine light at 90 degrees, as I said, atoms at odd and even sides scatter light with opposite phases, and they thus interact with light differently. So basically, this mask is realized automatically in this case. So you measure the atom number difference between odd and even sides, And this variable is perturbed due to the measurement. So the difference changes, and then the atoms start to oscillate. And in the case of fermions, if you measure the target magnetization, then this is the target magnetization which starts to oscillate and it gets its maximal value.
So if I understand correctly, then it's not so much that I'm detecting it, but it's more that it's interacting with even, the light is interacting with even and odd ones.
Not exactly, because so if you don't really count photons and don't record to which state do you project it, this would be a case of dissipation. So you can imagine so this is a single quantum trajectory. It corresponds to some particular number of photons which were detected at different time moments. Now, if you repeat your experiment, you will get a similar trajectory, but the phase of this trajectory will be shifted, and this shift is unpredictable. So now, if you average over all these quantum trajectories, which you can obtain in principle, you will describe dissipation, and so the interaction without the measurement. But you can already see if you average over all these sinusoidal functions, you will get a constant, because all sinusoidal functions will come with random phases. So in average, you will get 0. So in the number of atoms, in this variable, number of atoms, you will not see any oscillations at all, and you will not see this antiferromagnetic state. So only when you detect photons, you will project to the correct state, and the atoms will oscillate in phase with each other. And sometimes here they will reach its maximum, and for fermions, this would mean antiferromagnetic state.
I see. Thank you very much.
So we have another question. So Brian asked if the feedback-induced quantum phase transitions could be a topological one.
Oh, well, we did not consider this. This is a very interesting question.
So anybody else? Nope. Okay, thank you so much again, Professor Igor. Thank you, Santiago. And I'm going to switch to Spanish to make some announcements. La siguiente semana no hay seminario porque es el Congreso Nacional, entonces para que todos participen en el Congreso Nacional. La siguiente semana, es decir, dentro de 15 días ya vamos a volver a los seminarios. Y les voy a poner en el chat porque el 29 de octubre vamos a hacer una mesa redonda con 4 investigadores bastante bien conocidos, que es la doctora Rocío Jauregui, el doctor Julio Gutiérrez, el doctor Alex Franco y el doctor Fernando Rojas, para contestar las preguntas que los estudiantes de maestría, doctorado, licenciatura e incluso de prepa tengan acerca de la carrera de física o de ciencias en general. Entonces les voy a poner el link para que participen con las preguntas. Creo que ya es todo. That's it. Thank you so much again, everybody, for attending these meetings. I'm going to send you later the link for this seminar and those that happened during the month of September. Thank you so much, everybody.
Let's thank Igor for this wonderful talk. You know, like in the old way.
No.
Thank you very much.
Thank you so much. And see you, everybody, in 2 weeks.